Hello and welcome to 7.5. Today's lesson is looking at going from polygons to circles. We just discussed the last lesson about how you can kind of find different pieces of polygons from knowing things about the circle. But now we're going to go in the other direction. Okay, so in the previous task, planning the gazebo, you developed a strategy for finding the perimeter of a regular polygon with n number of sides inscribed in a circle with radius r. Tehani's strategy consists of the following formula. Tehani drew this diagram as part of her work as she developed this formula. So, using Tehani's diagram, explain in detail how she arrived at her formula. So I'm going to verbalize this and you can go ahead and write it down. So what Tehani did is she first found angle A by knowing that it is 360 divided by 2n. Okay, so she knows that let me get my pen out here. Angle A is equal to 360 degrees divided by 2 times the number of sides. Okay, now she also knows that x, that bottom side of this partial right triangle here, or of this smaller right triangle, she can find that by using some trig, which eventually gets down to x equals r times sine, the radius times sine of 360 divided by 2n. So we're looking at the hypotenuse of that smaller triangle times that angle measure, right? Or the sine of that angle measure, okay? Then finally, the perimeter of the actual polygon, whatever the n-gon is, she denotes that as 2n times x, okay? Where we have n as the number of sides and x as this right here. So we're going to simplify that by actually writing it out and saying 2n times r times sine of 360 degrees over 2n. Okay, so this is the value, or this is the perimeter of the entire n-gon. No matter what, how many sides it is or what the radius is, we can plug that information in and get our answers. So, since n is the only thing that really varies in this formula, because r remains constant, we're just changing the number of sides, Travis suggests that Tehani might rewrite her formula in this form instead, where 2r is on the outside, that constant, and then everything that is changing, so anything that's modified with that constant, is inside those brackets. Because the perimeter of an n-gon approximates the circumference of an area when the circumference of a circle, when n is a large number of sides. So as a polygon gets larger and larger, or the number of sides gets larger and larger, you're getting closer and closer to the circumference of the circle, okay? So the perimeter of the polygon grows closer and closer to the circumference of the circle. Now, Travis suggests they might examine what happens to that portion inside the brackets as n gets larger and larger. So use a calculator, or if you want to, if you're a Sheets whiz, you can use a spreadsheet to complete the following table to see what happens. So go ahead and pause the video here in just a minute and plug in these values for n and see what you get. So go ahead and pause the video. So hopefully these are the values that you found as you were plugging this information into your calculator. And what you'll notice actually is as we go downward, we get a funny, interesting trend, don't we? So we're going to keep moving on, noticing that trend. This looks familiar to me. Okay, so let's go on to the next page. And we need to write a formula for the circumference based on the circle. The circumference of a circle based on Tehani's formula for the perimeter of an inscribed regular n-gon and what you have observed while generating this table. So let's take a gander back here. We've got 2n times r times sine of 360 over 2n. So what I'm going to do right here is I'm going to use this idea right here, that isolation, where I know that this is the only thing that's changing, right? And 2r remains constant, right? 2 times the radius remains constant. Now, check out, as I go downward, that number is growing closer and closer to a number that I should probably be pretty familiar with at this point. I usually see it in a different form than that. I usually see it as the Greek letter pi, right? This 3.1415. As we get more and more sides, we actually grow closer and closer to that value of pi. So instead of representing this up here for the circumference, I'm going to actually just simplify it and substitute n times sine of 360 divided by 2n. That all really, as n increases, as n approaches infinity, we might even say, that grows closer and closer to pi with every increment of increase. Okay, so I'm going to take this, and I have found that the perimeter is equal to 2r times pi, which is very interesting because we know our our circumference of a circle to have the formula of 2 pi r, right? So that we can go ahead and write down for number 3. So now let's look at part 2. We're going to find the area of a circle based on the area of a polygon. So we just looked at the circumference of a circle based on the perimeter of a polygon, but now we're going to look at areas instead. So Tahani has a formula for the area of a regular polygon with n sides described in a circle with radius r, like this, okay? And that, again, just comes from trigonometry. If we want to look back at our circle here on the last page, all she's really doing is saying this whole bottom times the height, that is equal to the area of one triangle when you divide it by 1/2, because it's base times the height divided by 1/2. And then you're going to multiply it by n number of sides, okay? So n number of sides of the polygon, but then that means you have that many triangles within that polygon, okay? So she just used some trig and rewrote it in terms of these variables here, right? So what we found is that the angle, we're going to explain in detail here, the angle up at the top that we've discussed, again, we discussed this last time, the angle is equal to 360 divided by 2n, because you divide it into the number of sides that the polygon has, but then you divide that in half again because we bisected that angle with the altitude that we dropped, called h in this situation. Then we also know x is equal to r times the sine of 360 degrees over 2n. Okay, and that's found just by using some trig and then rearranging that trig equation. Then we also find the height of the triangle in a very similar way, but this time instead of sine, we use cosine because that's the trig function with the ratio of the adjacent side to the hypotenuse. So all of this is found just by trig ratios and plugging different things in. So then the area of this n-gon for the general polygon is equal to 2n times 1/2 x times h. Okay, so also I should denote up here, now that I have another a swinging about, this is angle A up there, right? And so this is the base of the triangle plus that 2 times, right? This is the height of the triangle, and then 1/2 the base times the height, and then multiplied by the number of sides and the number of triangles that I have. So now when I actually take what this is equal to and what this is equal to, and I substitute that in, I get, and I'm going to cancel this 2 and 1/2 off straight away, just it's easier that way to look at. I'm going to get the area of this polygon is equal to n times r times sine of 360 over 2n. Oops, 2n, not 20, times cosine, or times r times cosine of 360 over 2n. Okay, so there's my area, but again, Since I know that n is the only thing that's changing, I'm going to use any factor with n in it, and I'll kind of isolate that. And then anything that's not n, this r times r, I'm going to bring it outside this bracket, okay? So this is what Travis is suggesting right here. The area is equal to r squared times n times the sine of 360 over 2n times cosine this 360 over 2n. So now we're going to examine again that n portion, okay? So now again, I want you to pause the video and plug in all your n's for the n's in here. So plug in all those values in the left-hand column. So pause the video. So hopefully your values coincide with these ones that I have filled in on the table. And now we can write a formula for the area of the circle based on Tahani's formula. So again, as we go downward, check out what value we're approaching as n approaches infinity, as n gets larger and larger. Well, as we're going downward, we get closer and closer to pi. So what we're going to do now is we're going to write a formula for the area where this whole thing in brackets, we know as it gets larger and larger and larger, it's just going to be equal to pi. So we can substitute pi in for that whole thing. So pi is equal to n times the sine of 360 degrees over 2n times cosine of 360 degrees over 2n. And another way we can say this too is as n approaches infinity, okay? So that's going to be something too that you'll be familiar with as you get into things like pre-calculus and calculus. They are called limits. So we are going to take all of this and we're going to substitute pi in for that. So we get the area is equal to r squared times pi, which if you know the area formula for a circle, that's it right there. All right, so now that we're done with that first one, we're going to look at another approach to finding the area of a circle based on different shapes. And this is really where we derive the formula for the area of a circle. So we're actually doing the work that mathematicians did many years ago to find a formula for finding the area of a circle, because you can't just quite measure it. It doesn't work quite as well. So approach number 2 is circle can be decomposed into a set of thin concentric rings as shown on the left on the following diagram. If we unroll and stack these rings, we can approximate a triangle as shown on the right. So you can kind of see the shape of this right triangle here. Okay. Oh, that wasn't a great line. There we go, that shape. Okay, so there's this right triangle right here that we found. And when we're looking at the height of that triangle, the height is actually really just the radius of the circle. So I'm not even going to call it the height, I'm going to call it r for the radius. Now, and you can write that down for number 7, we describe the height as the radius, okay? Now, how about the length of the triangle down here on the bottom, this length? Well, if you think about that, that was the longest circle, which, or ish, it should be the longest concentric ring, right? Which is actually going to be the circumference. So rather than L, I'm going to call that the circumference of the circle. And we also recognize that the circumference of a circle is called, or is just pi times the diameter, right? Or pi times 2r. So as the rings get narrower and narrower, the triangular shape gets closer and closer to an exact triangle. So if we were to add or make these rings smaller and smaller, they would become more and more and more like an exact triangle. So as the number of rings increases, we would get more proper of a triangle as well. So what would this diagram suggest for the formula then for the area of a circle? Well, if we're thinking in terms of the area of a triangle, we know the area of a triangle is just the length times the height, or the base times the height divided by 2, right? So if we're thinking now in terms of the radius and the circumference, well, guess what? We have r times c times 1/2. Well, again, what is the circumference? Another way to write circumference is just 2 pi r. So guess what? I'm going to plug this in for where c is over here. And now I'll have 1/2 times r times 2 pi r Now 1/2 times 2 is just 1, so we can cancel those off. And when I simplify this and multiply r times r, I get r squared times pi. Guess what? That again is the derived formula that we found for the area of a circle. This time instead, though, we've been using a triangle to find that out. All right, let's look at approach number 3. Finally, we can decompose a circle into a set of congruent sectors like we've been working on in the past couple of sections. That's shown on the left, and we could rearrange these sectors, take them apart piece by piece, and approximate a parallelogram as shown on the figure, shown in the figure on the right. So this, we're pretending or we're enacting that it's a parallelogram. And you know what? As we make those slices smaller and smaller, these tops would get flatter and flatter, would seem flatter and flatter, and the height would get more and more vertical, right? And so the height here really would be this length, which if we look back to our original circle, that length is the radius, right? And then this piece up here, well, if we look at that, that's going to be 1/2 of the circumference, right? Because the other half is down here. So if we're looking for the height or the area of this parallelogram, we could define the area of as r times 1/2 the circumference, right? The base times the height. That's true of a parallelogram, that's true of a rhombus, that's true of a rectangle. That's the area formula for any of those figures. So now we've discussed the height of the parallelogram is the radius. The base of the parallelogram is 1/2 of the circumference. So now as we're looking for finding the area of that parallelogram, it's r times 1/2 the circumference. Now we've already discussed as well, just in the last approach, we said, well, the circumference is just 2 times pi times r. So if we plug that in again, very similarly to what we did last time, we get r times 1/2 times 2 pi r. 2 and 1/2 cancel each other off. Pi and r squared are left over. So the area of that parallelogram, which is truly just the area of the circle, is pi r squared.